Okay, this is the scope photo. I took a photo right off the scope and put it in my computer and blew it up. This is the AC input to the hemmorroidal transformer. And I do not have any cap in parallel or series or anything. It's just what it is. Meanwhile, in the secondary, there's about 5.2 watts being made of real power, which is a 50 ohm resistor with the secondary right across it, and it's making 16.2 volts AC. So it's about 5 watts output. Meanwhile, the input is this. Now, this is the phase shift. This one is the voltage. This one's the current. This one's the voltage. This one's the current. And you want to take your measurements at the zero line. For example, you want to know how many spaces from here to here of a sine wave. And that equals 360 degrees. This is the zero line in the scope. You know, that's this one. And so if you go here and you count, like let's say you take this voltage one and follow it up and then down, and then where it meets the zero line again, like this, it's 11 spaces. Okay, so 360 divided by 11 equals, I'm not sure. One moment. Okay, 360 divided by 11 is 32.7. So 360 degrees divided by 11 spaces is 32.7 degrees per space. What that means is, you see these little things here? There's 5 spaces between one square division, okay? So each of those represents 32.7 degrees. And there's 3 spaces from here to here. So that's the phase shift. So it's 3 times 32.7. What is that? 98.1. So it's over 90 degrees. But you know, it probably is right at 90 degrees. But it might be over. But it's up there at 90 degree phase shift. That means it's actually making zero. It's taking 0 watts. According to phase shift and power factor. So you'd call this a reactive power. Now, The reason for that is you can't have power unless you have both voltage and amperage at the same time. And you can see the only time there's both is this little triangle right here. So that's the input. Now let's say we're a little fuzzy on everything and it's actually 10. It's actually from the start, from here to here, it's 10. Now that would be 36 degrees per space. Obviously 360 divided by 10, and if there's still 3 spaces, let's say there's 2 spaces, 72 degrees, let's just say. And now what you do is you go to Google and you look up what is the cosine. It's spelled like this. What is the cosine of 72 degree angle? And the cosine, I know this, is 0.03. And the cosine is equal to the power factor. So when you have AC watts is volts times amps times power factor. So you see, if you have 0 as your power factor, you have 0. That's why 90 degrees is like the magic number, the target. If you have a 0.03 as the power factor, well, you get, like, let's say your volt's 120, and let's say your amps is 100 milliamps, let's say. So now you have 12. That's called volt amps. It's 12. Sorry, I'm writing while I'm looking on the camera here. Now you get to take 12. I'm going to look at what I write. 12 times 0.03 is actually the watts. You see what power factor does? If people say, oh, you don't have power factor in your equation, well, it actually makes it better. If there, it makes it less input. On the output, when you have a resistive load, there is no power factor because there is no phase shift. And what phase shift is here, let's say this is the voltage, channel A on your scope. And this is your current, channel B on your scope. That space right here between there and there, you take your numbers at the 0 line, remember? You don't do it at the peaks, you do it at the 0 line. That's your phase angle. And so that's what I see as 3 spaces right there. Right there. I see 3 spaces right there. So this is the input in AC to the hemmorroidal transformer, also known as a bit transformer, which is short for bitoroidal transformer, but there's no toroids in this thing. But there are hemorrhoids, so I call it a hemmorroidal transformer. Now, what was I going to do? Now, what you want to do to make it kind of real world, because so what you have a power factor of such and such. So what? The only people who are going to worry about that is the power companies, because they're supplying all these amps and volts to people, and they aren't being charged for it, because on the meter with a 90-degree phase shift, let's say your house meter will show 0 input, but meanwhile the people will be running stuff, or it'll show 72 degrees, or it'll show 50 degrees. So anything with an inductive motor, anything inductive will have a power factor to it. They have power factor correcting stuff, but basically what a power factor correcting is, you put a cap across the primary or the input, AC input. You put an AC cap across there and you find the right value where you lower your draw, bring it way down. So for example, this shows 30 spaces from peak to peak. And for the current, but now I'm going to change the photo to when I put an 4UF AC cap across the primary of this transformer. Now, this is what it's going to show. It's going to, on my tests with a meter, this kind of corresponded to 44 milliamps. And so you have it around up there, times 120. So volts input. So now if you put a power factor correcting cap across the primary, watch what happens. And I'm going to change the photo 1 minute. Okay, so this is that transformer, the hemmorroidal transformer, with now an AC cap across the primary, parallel to the AC input to the primary coil in the middle, the central coil, and the left and the right coils are the secondaries. And the secondaries are in series, and they make about 5 watts real power into a resistive load. So here is what happens. Remember the current before was like all the way up here, even with the voltage. And now it's dropped it down from here to here. It's almost, maybe cut it in half or so, what the amperage is going to be. And it's a little bit fuzzy. But now when you do your amperage, you would take the peak here and the peak here, and this is the peak-to-peak voltage that you need to know, and then you can put it in that formula. If you read all through my comments in the video before this, I explain it pretty good, how to do it. So you see, power factor correcting cap makes your watts input much lower because you've dropped your amperage way down. And note, actually this is what I wanted to show, is there's no real phase shift anymore. There's a little bit of one right here, but really the voltage and the amps are right on top of each other. There's the peaks. It's just a little bit of a shift this way to the current. Negligible. But that's what happens when you do power factor correcting. You make, they call it power factor is equal to 1. So when you do volts times amps times 1, you get just what the volts and times amps is. It will be what your watts is. And so this is 1 power factor, maybe a little bit over, like I'm saying, but not much. So this is with the volts and amps on top of each other, and it would look something like this with the output. When you have a resistive load, it just makes everything right on top of each other. There's no phase shift. So I wanted to show these 2 photos because my scope shots were so blurry and flashy yesterday. And so this shows what is going on. Now this is the grid input. I haven't redone the inverter input yet, but the inverter input is much different looking because it's like a DC spike, DC spike, DC spike, DC spike, and it's not the same as when you do a AC grid, but we'll see what happens with that. What I found is a cap in series, not parallel, raises the draw a whole bunch in amps, but it really raises the output even more. So I'll be doing that later. So, okay, I think that's about it. And if you want to be educated, if you don't know already about scopes and phase angles and how to measure current with a scope, go back 1 video and look in comments, and I did a big long thing about it all. Okay, thanks for watching.